So let's begin by recapping what we have learned so far in section 1.6. The first thing is that a basis beta for a vector space has two properties. One, it's linearly independent, and it generates the vector space. So if you have a linearly independent set that you can show generates V, in other words, you can pick an arbitrary vector in V and show that it can be written as a linear combination of the basis vectors, then you know that indeed that set is a basis. We also learned that beta is a basis for V if and only if each vector in V can be uniquely written as a linear combination of the vectors in beta. We learned that a finite spanning set can be reduced to a basis. Every spanning set contains a basis. And the replacement theorem, which the last video was just the proof of that theorem, just tells us that if you have a linearly independent set, and a finite generating set for a finite dimensional vector space, that the linearly independent set is always smaller than or possibly equal to the size of the generating set. And you can take vectors from G, the generating set, and throw them into the linearly independent set and create another spanning set the same size as G. We'll use the replacement theorem to prove some important corollaries in this video. In corollary 1, we are going to use the replacement theorem to prove that every basis for V contains the same number of vectors. So we'll start by letting beta be a basis for V containing exactly n vectors, and let gamma be another basis for V. And we're going to show, using the replacement theorem, that gamma and beta contain the same number of vectors. Suppose gamma contains more vectors than beta. Well, then we could take n plus 1 vectors from gamma and call that linearly independent subset. Let's call it L. Well, L is a linearly independent subset of V, and the span of beta is all of V. So we have a linearly independent subset with n plus 1 elements in it, and that has to be less than, according to the replacement theorem, the number of vectors in a spanning set. Well, beta has n vectors, and n plus 1 is not less than or equal to n, so we have a contradiction. If gamma contains fewer vectors than beta, then the same argument holds in reverse. Therefore, we can say that gamma has the same number of vectors as beta. In other words, any two bases for the vector space has exactly the same number of vectors. I might note here that we went through proving the replacement theorem, which seemed, you were probably wondering why, and you can see that this is the reason why. We use it to prove some very important results in linear algebra. A vector space is called finite dimensional if it has a basis consisting of a finite number of vectors. The unique number of vectors in each basis for V is called the dimension of V, and it's denoted by dim V. A vector space that is not finite dimensional is called infinite dimensional. In our course, we're only going to be working with finite dimensional vector spaces. So let's look at some examples of vector spaces and say what their dimension is. We know that the zero vector space is generated by the empty set, so we would say that the dimension is equal to 0. Rn, the set of n tuples, well, let's write down what its basis is. Our author calls them E sub I, where E sub I is the n tuple of all zeros that has a 1 in the ith position. So E sub I, I'm just going to write it like this: 0, 0, 0, dot, 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 1, dot, 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 0, 0, 0. 1 is in the ith position. That's not a very good way to write that, but I skip all the words. And so we would say that its dimension, the dimension of n space, is n. We have n vectors E sub I. The set of m by n matrices is generated by a basis. E sub ij is the simplest one, and E sub ij this is a matrix that has all 0 entries except 1 in the ijth position. In other words, the ith row, the jth column. And of course there would be m times n of those. So the dimension of the vector space of m by n matrices is mn, the product. The vector space Pn of R is all polynomials of degree less than or equal to n with coefficients that are real numbers. So a basis for this would be the set of vectors x to the n minus 1, dot, 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 x squared, x, and a constant. I'll just make it 1. So the dimension of Pnr is equal to n plus 1. Now, here we have the set of all polynomials with real coefficients. So this is an example of an infinite dimensional space. We have 1, x, x squared, x cubed, and all the powers of x. So we see that this is a infinite basis. It is countable. In other words, it is one-to-one correspondence with the natural numbers, but this is infinite dimension. The next example is the complex numbers over the field C. Well, this is dimension 1. Here is the basis. If the field is the set of complex numbers, then if you just have 1 and multiply in from the field, you get all of the complex numbers. But if our field was the real numbers, well, then we would have a dimension 2. And here's the basis, 1 and I. Be sure and see how the field enters into the determination of the basis. So here is the second corollary of the replacement theorem. Let V be a vector space with dimension n. Any generating set G for V contains at least n vectors, and a generating set for V that contains exactly n vectors is a basis for V. Well, this is just a result of Theorem 1.9. Since G generates V, we know G contains a basis beta for G. Well, that means that the order of beta, which is n, is less than or equal to the order of G, using the terminology of group theory. So n is less than or equal to the number of elements in G. And if the order of G, or the number of elements in G, is equal to n, well, then beta is equal to G. Part B, any linearly independent subset of V that contains exactly n vectors is a basis for V. Well, let's let L be a linearly independent subset of V containing n vectors. And let beta be a basis. Now we know that V has dimension n, so we know there are n vectors in beta. Okay, so we know that beta generates the vector space, and L is a linearly independent subset of V. So therefore, there are exactly n minus n vectors, in other words, 0 vectors, in beta that we adjoin to L to get a generating set. Well, we're adjoining no vectors to L. H is the empty set. So we have proven that L by itself is a generating set by using the replacement theorem. Once again, think how we're using it. L is a linearly independent subset of V, and it contains n vectors. Beta is a generating set for V. So by the replacement theorem, we would take exactly n minus n, or 0 vectors from beta, to make L become a generating set. So L is, and any generating set that contains n vectors, the dimension, is a basis. Part C, every linearly independent subset of V can be extended to a basis. So let L be a linearly independent subset containing m vectors, and beta be a basis. So we know beta contains n vectors. By the replacement theorem, write this out, by the replacement theorem, RT, we can take exactly n minus m vectors from beta, the generating set, and put them in L, or adjoin them to L, to get a generating set. Well, this generating set has exactly n elements in it, so we know that by part B, it is a basis. That set has n vectors, so it is a basis. So anytime you have a linearly independent subset, you can always assume that you can adjoin vectors to it to come up with a basis. The dimension of subspaces, I'm sure won't surprise you, is always less than or equal to the dimension of the vector space. But let's prove that. Let W be a subspace of a finite dimensional vector space V. Let's let the dimension of V be n. Now if W is equal to the trivial subspace, then the dimension of W is equal to 0, and of course 0 is less than n. So we can assume, or we can, let's not assume, let's say we can let V be in W. So we have a set V, and that set is linearly independent. Any set of one vector is. So I can choose another vector. Let's call this vector V1, the first one we chose. So we can choose another vector, any one that isn't a multiple of V1, and put that one in. And that set is linearly independent. And we can continue choosing vectors that are linearly independent with the ones that we've already put in. Now granted, in reality that may be very hard to tell, but we know that either V3 can be written as a linear combination or it can't. So you can always keep picking one that is linearly independent until you have to stop. So let's say we go up to the kth vector, and then if we add in any more v sub k plus 1, then it is linearly dependent. In other words, we go to the point where we have to stop, because any vector that we put in further than that will be a linear combination of the first k vectors. Well then, any vector W in the subspace is a linear combination of V1, V2, and v sub k. So therefore, the dimension of W is equal to k, which is, of course, less than or equal to n. So now we're going to look at some problems from the text. Number 4, at the end of section 1.6. Do the polynomials, these three polynomials, form a basis for the vector space of polynomials of degree less than or equal to 3? Well, we can say no right away, because the dimension of P3 with real coefficients, is equal to 4. So 3 vectors will not form a basis. But they would be the basis of a subspace. And what would the dimension of that subspace be? Well, let's say, let W be the span of, and I'm going to give these a name. Let's call this one P1 of X, and P2 of X, and P3 of X, just to save time. So let W be the span of P1, P2, P3. So it is a subspace. We know it's not all of V because the vector space has dimension 4. But what is the dimension of W? Well, the dimension of W, you can quickly see, is equal to 3, because P1, P2, and P3 are of differing degrees, one of degree 3, one of degree 2, and one of degree 1. And you know that one could not be obtained as a linear combination of the other two. So the dimension of W is 3. This problem, number 12, is like one that we did in class. Let vectors u, v, and w be distinct in a vector space V. Show that the set containing u, v, w is a basis for V. If it is, then these three vectors comprise a basis for V. The vector u plus v plus w, v plus w, and v. Okay, so we are assuming that this is a basis. So what we know from that is, we know that if AU plus BV plus CW, where A, B, and C are from the field, is equal to the zero vector, then we know automatically that A equals B equals C equals 0, because they are linearly independent. What we want to show is this. We want to suppose that we have a linear combination of these three vectors. In other words, suppose that, I'll call them something else, D times U plus V plus W plus E times V plus W plus F W is equal to the zero vector, and we have to prove that D, E, and F are all 0. In that case, the three vectors in question are linearly independent. Well, let's multiply it out. You do that quickly, and collect like terms. So I rewrote the linear combination above as a linear combination of u, v, and w. Well, we know that those vectors are linearly independent, so this implies that D is equal to D plus E, the coefficient of V, and that's equal to D plus E plus F, the coefficient of W, is equal to 0. And why? Well, because of this. We have written it as a linear combination of u, v, and w. So we can set those coefficients equal to 0. Well, if D is equal to 0, and D plus E is 0, then E is equal to 0, and if D and E are both 0, F is equal to 0. So we are done. So in problem 13, the set of solutions to this system of linear equations is a subspace of R3. Find a basis for this subspace. Well, what I want to do is I want to turn this into a system of simpler equations to look at, so I can characterize what the vectors are like in the subspace. So instead of adding equations together and switching places and multiplying through by constants, I'd like to just get rid of the x1, x2, x3. And so I take the coefficients and put them into a matrix of coefficients. So we have 1, -2, 1, 2, -3x2, 1x3, and our constants on the other side are 0. So the first thing I want to do, I want a 1 here, and I've got it. So I'm going to multiply the top equation, really, by -2, and I'm going to add it to the bottom equation, or the bottom row if we're in the matrix. So I get, my top row stays the same, and the bottom row, I'm adding the top row times -2, so I get 0. That's what I wanted. Then I have 4 plus negative 3 is 1, and negative 2 plus 1 is negative 1, and 0 stays the same. So now I want to get a 0 in this position. I have a 1 here, and that's what I wanted. So I'm going to multiply that bottom row just by 2 and add it. That will give me the 0. So my next matrix will be, well, the bottom row is the same, 0, 1, minus 1, 0. Now I'm multiplying it by 2 and adding it. Well, 1, and then I get my 0 that I wanted. 2 times negative 1 is negative 2 plus 1 is negative 1. And so this is much simpler now. I can see the relationship between my x1, x2, x3 better. Here I have a x1 minus x3 is equal to 0, and x2 minus x3 is equal to 0. So we can see that, well, x1 is equal to x3, and x2 is equal to x3. So what we have is all vectors where x1 is the same as x2 is the same as x3. So a basis for this would be simply the 3-tuple 1, 1, 1. Multiplying in from the field of real numbers, we get all vectors that have the same first, second, and third entries. So the dimension of this subspace is 1.